On the 31st of January 2021, with the help of physicists and engineers from ALICE, a live broadcast was transmitted from the very core of the ALICE experiment at LHC Point 2 at CERN. After a virtual tour showing and describing the sleeping machinery of the ALICE experiment, the scientists discussing the event answered questions. Luckily, among the answers were also those asked on behalf of user zombiekanapa.
Which brings us to the question from zombiekanapa, which is:
which research has generated the most response from the scientific community in recent months?
Since LHC started, the result that had the biggest, that was the most impressive, I guess, was the discovery of the Higgs boson. There were also discoveries of other particles that were foreseen by the theory but hadn't been seen before, like tetraquarks, pentaquarks, and so on. These are from the other experiments. For ALICE, what could we see? What has generated the most response? Certainly something that, at least for the scientific community, was a surprise when it was first observed. And that was observed even before LHC had started by other heavy ion experiments at RHC, the Relativistic Heavy Ion Collider in the United States. That was the fact that this exotic state of matter, the quark-gluon plasma, which normally one would expect to behave like a gas, because plasma normally is something where you have a free constituent, so you expect them to be uncorrelated. Anyway, it was observed that this quark-gluon plasma behaves like a perfect liquid. And this was first observed at RHC, and then it was confirmed at LHC. So this was, let's say, a surprise when we first saw it. Another result that I mention it because it is in the Guinness records, and again it was there first from RHC, and now we have the record that with these heavy ion collisions we create the highest temperature on Earth, which is trillions of degrees. And this is the collision at the moment of the interaction, which of course we don't measure with a thermometer or anything, but we measure indirectly, for instance, from the photons emitted as this initial state cools down. I don't know what else.
But for another thing that impressed me a lot was the fact that we could see quark-gluon plasma also during proton physics, which was something we didn't expect. And instead, it was found and confirmed by ALICE that quark-gluon plasma is also there during normal proton collisions, where in principle we were not supposed to find it, and instead we saw it, although in much less quantity.
Is there any point in continuing to search for dark matter according to current assumptions, or is it time to seek answers to this question by testing radically new, bold, or even revolutionary hypotheses?
Or is it time to seek answers to this question by testing radically new, bold, or even revolutionary hypotheses?
It's not easy, because if I knew the answer, I wouldn't be here. Let me say, with what we have today available, we are doing the best. It's impossible to do better research on elementary particles than what we're doing here at CERN for what can be created in laboratory, of course. There are other experiments. For example, there is AMS, which is installed on the space station, which is doing research mainly for monopole magnet. And that is something that can be done only in a space for several reasons, or experiments which are on the gravitational waves, which are based on big distances, therefore at CERN is not really possible to do. So with what we have today, if you want, we are doing what can be done. New revolutionary hypotheses may need new revolutionary detectors, and this is not easy to do. Said that, at CERN there is an activity going on, which is the Future Synchron Collider, which will return to the same physics which was done in that area, which is the electron-electron collisions, and that will become operational in 15-20 years, at least it will start working in 50, it will start being prepared in 15-20 years. I don't remember now exactly the time scale, and that will be a big change. It will produce a new type of physics that has never been studied before.
If I can say a bit more about the dark matter, certainly we are looking at in different ways. Since we don't really know what it is, we don't know how to look. But certainly in addition to the accelerator experiments, which look for dark matter, for example, one possibility is if a theory called supersymmetry, which up to now has not been proven experimentally. If this is proven experimentally, this might explain dark matter. Anyway, there are experiments which do not use accelerators, which hope to see dark matter based on scenarios like that it is made of something called WIMPs, weakly interacting massive particles, and so on, without using accelerators.
But this is based on astronomical observations, I suppose.
I wouldn't call it astronomical. I'm referring, for instance, to an experiment called Dark Side that is being prepared now to look for these WIMPs and so on.
Interesting.
Lunar accelerator.
This is also why I was talking about astronomical. There is a question from Brandon, if lunar-based accelerator is in our future? The answer is unfortunately not. Because as you saw, the LHC is a big structure which needs to be served. So you need access, not all the time, but fairly often. And also you saw the size, you saw the weight. I don't think that it is a target for the first or even for the second generation of moon bases to provide accelerators. Where it could be interesting maybe is the study of things which are detectable only in the cosmos. So for this we need smaller equipment and even equipment that can be transported easier, such as, take an example, AMS for the space station. An accelerator in space, seeing the size and seeing the resources which are needed, electricity, gases and all the rest, I don't think it's a feasible target for the next century or so, or even further down.
Is artificial intelligence, machine learning, and quantum computing involved in the processing and interpretation of data obtained during experiments?
Okay, here we are talking about the processing of the data. The answer is not yet, but there are many activities at CERN to study the possible application of machine learning, quantum computing, but at the moment is still at the very preliminary phase. So for the moment we are still based on traditional techniques, although for run 3, Alice will use data acquisition techniques which will be brand new, and it will use no longer CPUs but most GPUs for the data processing. This is because one of the main activities that we do in the reconstruction is to do tracking. In other words, we have a series of points and we want to find the track that fits the points, and this for thousands and thousands of tracks. And this is where the graphical processing in the GPUs can be very useful and very fast. This is the big step forward for Run 3. So for what concerns machine learning, there are projects for machine learning, not much in the reconstruction, but more in the mining. Because Alice, as all the other experiments, they will create billions and billions of photos of events that will have to be reprocessed. So machine learning could be interesting, for example, to tag these events, to find the features which are interesting, and then to mine in the enormous amount of data that will be taken to extract all the important things for a particular type of physics.
Album of particles available at